Okay, so today's we to start the deep questions there, and first question is house robber there, lead code number 198. So here I can summarize this question. Here basically we are given an array and where each element has to represent money in a house. The constraint is we cannot rob two adjacent houses because the alarm will trigger. So at every house we have two choices: either we have to rob that current house or either we have to skip that house. So in case we have to rob that house, we must skip the previous house. Okay, and in case of skip house, we simply move to our previous house. Like we have both of the choices: either we have to start from the starting of the array or we have to start from the ending of the array. It doesn't matter there. Basically we have to traverse from the array from one end to second end, and it should follow the constraint that it has only two options there: either rob the current house or either skip the current house there. So since at every index there we are making a decision like between two choices, so basically it gives me the intuition if we have multiple choices at any index here, so we should go this naturally leads to recursion decision process basically. So so far every house we ask what's the maximum money we can collect if we consider house up to this index. Like we can go in this manner, we have to say how many of the maximum amount of money we can rob there up to this index. Okay, so what it's meaning, simply since we should go for the recursive side, so how we do this? Let's say first of all I can say let's I'm talking about this wait a second. Okay, so if I'm talking about this test case there, okay, so here it is given for this test case. First of all we have to define I make first of all the recursive tree there. After it I have to define what's the question there. So basically I use the f of I, which is our recursive function. What it say? It say that it is the maximum money from index is equal to wait a second, I have to grab this part here. Okay, so yeah, there's this index, how it is goes on, this goes on till to index number 0 to I. So basically this is the definition of f of I. This is basically we have to define this recursive function. Now I draw the recursive tree there, then I explain you like how to we can optimize this or another goal. So like this is our simply recursive function. What's our final goal there? We have to find the f of n minus 1. Like we have to start from the starting of the array, and we have to reach the up till the end of the array. Okay, n minus 1 is basically this size is simply index there, and we have to reach the end. So this is nothing but we have to find f of n minus 1 there. So yeah, okay. So like first of all, if I have to talk about the brute force, if you have to say let any at of index, we have two options: either we have to rob or either we have to skip. So we can say one thing there, what is the option number one there? We can do this in take and non take part there. So what is in this? If we have to rob this part, so we can use its money there, and after it we have to go to f of f, let's say we have to start from the ending, it doesn't matter there. So okay, if we have to start from the ending of the array, and if we are standing at I index there, so first of all what we have to do, we take its money there, and then we have to go to f of I minus 2. This is the take condition. In case if we have to just skip this part, so we simply directly go to this part, f of I minus 1 there. Okay, so these are the two basic conditions there, and in both of the condition we can simply do there, we can say f of I is nothing but it is simply the take comma not take there. So these are the two condition, and we have to simply return this condition, and we have to use return at end of the array f of n minus 1 there, because we have to start from the f of n minus. That's why I have to start from this. Wait a second. Okay, so I have to start from this I is equal to n minus 1 there. If I have to use recursion from starting from there, I have to reach to starting of the array. And like also concerning about the constraint that it doesn't go below I is equal to I is equal to 0. Okay, so like let's say if I have to talk about this test case there 1 2 3 comma 1. So how we do this recursive tree there? So let's have to like first of all minimize this part. Okay, like if I have to start from the f of 3 there. Okay, so what we do there? So there are either the two conditions there. Let's say I have to draw this okay, so from f of 3, what are the possible cases? Either we have to go to f of 1 there, or either we have to go to f of 2 there. Okay, so this is the case if we have to select this. So if we have to select f of 3, so we should we are not able to allow to pick its consecutive means f of 2. So this is the condition in which we have to skip that part. Means basically it is the condition where we take the part there, and it is the condition where we not take the part there. Okay, so similarly we extend this recursive tree there to below part there also. So okay, okay, and here at left side we have to take. So if it used to stick the f of 1 there, so it has to skip the f of 0 part, means it goes to f of minus 1 there. Okay, and like similarly if it is skipping this part, so it goes to f of 0 part, just it's below house there. Okay, similar conditions this is goes on. Like I have to extend this part there. So this is f of goes minus. So what are the possible cases there? This is f for 0 there, and what it is nothing but f of 1 there. Okay, now again expand this part there. Since we can do wait a second there, I explain you what the use of a necessity of basically dp there. So that's why I have to draw this recursive tree there. So f of minus 1 is hearing, and here if in the else condition there, it is simply goes to the 0 there. Okay, so I read there, it is simply the take part there, and it is simply the not take part there. Okay, so this is a complete recursive tree there. We see one thing there, whenever we have to draw this recursion tree, we see one thing like there are some of the overlapping cases there. There are basically some of the overlapping subproblems there. If we have to solve for this tree, then goes to this, then goes to this, we see one thing there. There is a f of 0. If we have to solve for this f of 0, so this doesn't necessary to solve again the things for this f of 0. Similarly, this f1 case and this f1 case repeats again there. So basically there are just nothing but overlapping subproblems there. So we don't need to separately solve for the each of individuals. We just need to memorize this, or we can say we just need to remembering things and use to store the previous value in the final upcoming value there. Okay, and see one thing there also, since we have to start from the starting of the array there, and we have to go to the starting ending to starting of the array. And since the starting there, the index number is equal to 0, so we don't go for less beyond the index number 0. So that's why in case if we have to face any kind of the negative index, we simply stop there. Basically this is nothing but our simply base case there. Okay, now we see one thing there, we see I have to explain you there are multiple cases there, f of 1 there, f of 0 there. These are appears multiple times there. So what it means, this means that same subproblems are being recomputed there. So basically this is a simple overlapping subproblem. So by this gives me hint that we should go for storing this, and what we call for storing, basically this is nothing but dp. Okay, So like simply first of all we go for the brute force there, then we go to the DP questions there. Okay, so like we brute force what's the code there. There's a main function there in which it has to pass the vector in the original question there. We define first of all its size there, then we call the solve function there, and it is start from the ending of the array. Now the definition of the function is there's the index parameter passed there, there's the original vector passed there. There is a base case condition. If I is less than 0 means if I is goes less than 0, so it is the invalid case. So in that case we have to return simply 0 there. Why return 0 there? Because and whatever the case, simply we have to take maximum part. So if any of the becomes 0 there, so we simply exclude that part. So that's why we have to take return 0. So there's a two condition there in take part and non-take part. Take part means we have to take the current position and we have to go by skipping just consecutively and go to the just if we have to start for, if we have to call for I, so we should go for the I minus 2. Similarly for the no take part, there's we go for the I to I minus 1. So that's why, and we have to simply return the maximum to take or non take. So this is the brute force there. But there's a one thing there, like what's the time complexity here. So you see one thing there, we have to talk about this test case there. For each of the index we have the two options there, either we have to rob this part or either we have to skip this part. So we can say like is since each element has two options there, and how many of the elements there, there are nothing but n elements there. So basically we can say the overall time complexity is going exponentially. It is nothing but all 2 power n there. This is the time complexity there. And what's the space complexity for this? This is nothing but of n for the recursive stack there. So now we see one thing there, when we go for its constraint part there, we see it is 100 there, size is goes till 100 there. So if we go for the brute force there, so it 2 powers 100, so it exceeds our time, so it gives you TLE. So that's why I already learned this code there. So there's the cases where it gives a TLE cases. Okay, I write there also. If you go for the brute there, it is nothing but of 2 power n there. I don't know how to, like you so okay, so this is nothing but so this is the time complexity for this. Okay, so like we see there that time complexity is such use. So this brute force is the phase there that gives the TLE there. So to avoid the recomputation here, we should go for the since we have to store the results there, and what is basically known for this storing process, so this leads to the DP, basically memorization part there. So we should go for the better approach. So what is this in this approach? Here we do nothing but we simply return the store the result of every of f of I, so that it has to compute only once there. Okay, and in the case if we need to count if we need to use of f of I, we simply used our previous stored answer for or f of I in the future cases also. So that's why this is the DP approach. So this is nothing but there's the I already solved there. So this is the DP questions there, DP method there. So here I use the memorize part there. Like for the interview purpose, we there's no need for unless necessary, there's no need to go for the tabulation or space optimized part there. But in my future videos, I also explain the tabulation or space optimized part also there. But we have to concern about the memoize part there. So here what we do, simply this is the initialization. Here we I have to define the vector DP vector there, and simply return the return solve function there, where simply pass the index enums, and there's a DP vector also there. Okay, this is the base case there. Now if we have to check if in case we have to find DP's non-empty, where means this is already we have to already compute this, so we simply return that DP value there. Again the two cases there, that the take case there, the no take case. and in the we simply at each index we have to store the maximum value of both cases and simply return the dp of I value. Okay, so like since this is goes for the n minus 1, so this return for the dp of n minus 1. So dp of n minus 1 is nothing but the dp vector where index goes to 0 to n minus 1 there. Okay, so what's the time complexity for this? So the time complexity for this is there's a O of n. Okay, uh, like by is it's of for n, so it is nothing but the due to this dp vector there. What is the space complexity of here? So it is like often it is for the recursive there, and there's of n also for the this using of this dp vector, so that's why, but approximately we can say the of n there. So this is the, and again like we also have to, there's no need to optimize it further in the interviews purpose, otherwise we can do this part. So for further optimize we can go for the bottom up dp, which is also known as a tablet part, and it is further enhanced optimized by the space optimizer, but we don't have to concern about this. So that is the our question there.